Okay, specific heat of an unknown metal. This is the post lab. So hopefully you learned how to run a water bath. Academic kids, you had 3 runs with zinc, and honors kids, you have 3 runs with zinc and your unknown metal that you get to identify. Okay, so we did all that, and let's talk about results. All right, so this is for the academic students. This is how you will do your calculations. We're going to use a formula called Q equals MC delta T, and Q is referring to our energy. M is our mass, and it'll be in grams. C is a specific heat. This is a constant, and its units would be joules, grams, degrees Celsius. I forgot to tell you that energy will be measured in joules. And the last one in this group is your delta T, which is temperature, and it's always going to be final minus initial. Okay, so we always do final minus initial on that. Now, for what we're doing, we had the metal was in a hot solution, getting energy from the water, and we had in the calorimeter cup, we had the cold solution. And since the hot is going to lose energy to the cold, we're going to put a negative sign out front. Okay, specific heat values have to be positive, they cannot be negative. So I have Q hot equals to Q cold. The Q hot's our metal, the Q cold is our water. So what we're going to do is we're going to have the mass of our metal, C of our metal, that's going to be our X, right? And we have delta T. Then we have the mass of the water, the CW of the water, and the delta T of the water. All right, we have everything on this side. So let's go look at this side real quick. If you go over here, you had 100 milliliters, and if we recall from what we did at the beginning of school year, the density of water is 1. So if the density of water is 1 and I have 100 milliliters of it, I have 100 grams. Okay, this number here, this number is set. Everyone will use 4.18 joules per gram degree Celsius. Everyone uses that number, right? The next set of numbers comes from your chart. This is your max and min from your chart. So when you did your statistics on your graph, you got those numbers. So over here, it's this number, that's my initial, and this is my final. So I'm going to take final minus initial. Okay, so then let's go look at our metal side. I know that I have 13.56 grams, which is this one right here. CM is my unknown. I can leave it there, or if you prefer, you can write X on there instead. Our final temperature, as you saw with the water, is 22.5, and we're assuming that it started at boiling point, which is 100 degrees Celsius for water. So it's going to be minus 100. That is also here on your chart. And if you remember, everything across the chart right here should all be the same, 100 degrees. Once I have that, let's get this side to a whole number first. So I do the multiplication of that. I'm going to get 836. Okay, then I'm going to do 13.5 times the difference of 22 minus 100. That's going to give me a negative number. So when I do the multiplication, I get 1050.9. I'm going to keep my square brackets on here, and I'm going to make sure to bring down my negative, because when I do a negative times a negative, I'm going to get a positive. Since this is my X, I need to isolate it. So I'm going to divide out that 1050.9, which is now positive, and bring it over here. When I do that math, I get CM equals 0.8. Now, we were working with zinc. Zinc's accepted value is 0.38. And it's in the notes. So I'm going to take my accepted value, 0.08 minus 0.38, divide by 0.38 times 100. And I'm going to get, for this team, they had 110% error. Okay, So that is your calculation for the academic side. Honors, you have a little bit more on yours because we're actually going to look at the whole system that we're working with, okay? So not only do I have the metal and I have the water, I technically have the cup and the stirring rod because they were in contact with the water as you were doing your reaction. So same start as we saw. I'm going to have my numbers that we saw earlier, the 13.6, which is the metal, the 22.5 minus 100, that's going to give me a negative number. Okay? Now, the mass of the water, as we saw before, is 100. We are all going to use this 4.18. That is set for everybody. Now, as we did before, 22.5 minus 21.2, that all came from our chart over here. Okay? Now I need to include my cup. So this is where these numbers down here come in play. So for my cup is 20.15. So I'm going to put that number in. Everyone's going to use this 0.91. The reason is the specific heat of that cup is set to be 0.91. The temperature of this will be the same as the temperature change of my water. That doesn't change. Then I got to go get the mass of my stirring rod, which is 11.70. Okay. And, whoops, I'm going to put in there. Again, the stirring rod, technically is a majority of it is aluminum. So we're just going to go forward with our aluminum number, 0.91. And again, same temperature as the water. So these are all the same because they're on contact. Now, this is a long problem. So I suggest you get 100 times 4.19, all this, get this operation done first, and this will give you this number. Do this operation here, and I'll get this number. I'm going to break this down. I'm going to do this one, and I'm going to get this number. I'm going to step through that one at a time because otherwise I can get a wrong number. I'm also going to take this 13.56 times the difference of 22.5 minus 100, and I'm going to get that summed to number 2. But I'm going to leave that sitting until I get this side here now summed to a whole number. So I'm going to sum this number up, and I get 581.08, just as we did before. We've now got to isolate our CM. So a negative times a negative gives me a positive. So I divide by the 1050.9. And I'm going to get for this one, CM equals a 0.55 joules per gram degree Celsius. And that's okay. I'm going to do my percent error on it again. We're all going to use this 0.38. Everybody uses that number because that's the accepted value of zinc. And we're going to do 0.38 minus your number divided by 0.38 times 100. And that tells me this group had a 44% error. You're going to have somewhat a large percent error with zinc because zinc loses energy very easily because it has a low specific heat. That's why you had to move fast as you went from one to the other. Honors, I'm providing this in there too because it's a little bit larger font for you so you can kind of see a little bit better. Also honors, there were 3 metals. Okay, now over here there were some values of interest. Okay, this is not all of them because you need to check for copper and lead and find out what the specific value of those are. And one of those is copper, one of those is lead, and one of those is aluminum. That was the 3 unknowns. So hopefully when you do your calculations, we can look at your number and we can match up to what it's supposed to be. Okay, so honors, you have 4 calculations to do, 3 for the zinc, 1 with your unknown, and you're going to try to identify your unknown, not necessarily always on the physical characteristics you saw, but also on the quantitative value that you got from your lab. And if you are in need of extra data, just in case maybe you ran short on time or something, there is extra data as well for you there. There's your analysis. Pre-AP, we've already handled your extension. Okay, so you are not determining the actual specific heat of the coffee cup because we use the calorimeter cup. Okay, just do the unknown metal. And chemistry, I did not give you unknown metal, you just have zinc for academic. Okay, few things. This is our equation, Q equals MC delta T. Q is our heat energies, mass is M, C is specific heat, delta T is temperature. Okay. Specific heat value is how well it holds on to heat. So we talked about that before. If you want to be dumped with a hot pan of water, or if you want to wait till it cools off. Water has a high specific heat. It's one of our highest ones. And then you can see on this list here, because I know some of y'all will need this, especially honors. There's your lead. There's your copper. And there's your aluminum value. Okay? So those of you who don't need that. Heat transfer, we're doing law of conservation energy. So energy is neither created nor destroyed, but it's being transferred from one to the other, and that's what we're seeing. So just as we had law of conservation mass, same thing with energy. It's being transferred. So it goes from a warmer to cooler object, and you guys all know that from what you're doing. And that is it. Live long and prosper.